Now my pleasure to present Brian. He was already on the TST panel, so.
Yeah, so Andrea and I are going to spend the next about half an hour, maybe a little less, talking about the southbound and northbound interfaces. And so, all right, so what we mean by northbound and southbound is the interfaces by which you can interact with the control surface or the controller from outside of ONOS, the piece that Thomas just talked about. And so northbound is typically what we talk about for clients, for applications, user interfaces, etc. We typically talk about southbound for how we interact with the environment, the devices, how we discover information about the environment. But from the perspective of the software, this boundary is kind of arbitrary. We just use northbound and southbound because their purposes are slightly different. So northbound just means how we talk up to orchestrators, to clients, to applications. Southbound is how we interact with the environment. So on the northbound side, I want to spend some time talking about three major areas. One is the core abstractions that ONOS makes available. I'll talk about topology, network programming, and network configuration. Some of the external interfaces that ONOS provides for those core abstractions, and then also how the northbound can be augmented by applications. So as Thomas mentioned, and as you probably are familiar with, ONOS has a number of configuration and control abstractions. The idea for the northbound is that these abstractions are as device independent as possible, and in some cases even topology independent. So these are part of the core, and then they're exposed to applications that are running on ONOS directly, and they're also exposed via other protocols. So on the topology front, we have a directed cyclic graph made up of infrastructure devices, infrastructure links, and hosts. So there's a fairly simple model for each of these things in ONOS, but if you have a more complicated representation, there's a mechanism we have called projections, where you can, in Java or in the JSON, you can see, actually I don't know if you can do it in JSON, it would be easy enough to extend, but at least in Java you can cast these basic models into more specific models. So for example, if you have an optical device or you have an access point, a wireless access point, where there's additional attributes that you want to be part of the model, you can extend the model, and then your applications that are aware of these particular parameters can cast the model to the appropriate thing. So topology, I think, is fairly straightforward, sort of the logical graph. The one other thing I'll mention on the topology front is that there's this notion of virtual networks or virtual topologies. You could think of these as slices, or you could think of them as transformations of the topology. It's a work in progress for one of the brigades, but the idea here is that there's a physical graph. That's the topology you'll get out of ONOS's topology service. And then there's also an opportunity to provide views of this topology or abstractions of this topology to external tenants or applications. On the flow programming front, there's 3 levels of depth here. Each provides a different abstraction. The first is flow rules. So what flow rules do is they provide protocol independence, the ability to program match action style rules against a data plane flow table in a way that's independent of netconf or OpenFlow or any particular OpenFlow version. Building on that level of abstraction, so building on the protocol independence, is pipeline independence. So every device or OpenFlow-like device where you have control of flow programming, or even in some cases netconf devices where you have control of the ACL table, is going to have a different pipeline where certain types of rules can fit into certain stages of the pipeline. Certain things need to happen before other things. And flow objectives is you can think of it as an ONOS pipeline, fairly abstract ONOS pipeline that you can program against. And then we have a sequence of drivers we call pipeliners that do a transformation from the ONOS pipeline to your device-specific pipeline. So what the flow objective abstraction provides, just to summarize, is pipeline independence. So you can program a flow or a set of flows against a device rather than having to think about the individual nuances of the pipeline in those devices. And then a third level of abstraction we provide is topology independence. So the ability to not necessarily have to think about if I need to provide service from one side of my network to another side, a virtual port or a physical port to another port, not having to do a path computation, not having to select a tunneling mechanism, not having to individually get the resources or program to each of those devices, but rather to specify at a high level what the policy is as far as connectivity is concerned, and then letting ONOS take care of path selection, resource reservation, and resiliency. So just to provide just a picture to help solidify this, we have a whole bunch of southbound protocols that devices use, OpenFlow NetConf TL1, different versions of each. Each of those would need to be, you would need to speak a different dialect in order to take your match action style rule and push them down to devices, but flow rules provide that abstraction. On top of flow rules, we have, for each of these devices, different pipelines. Here's an example of 3 of them. There's dozens more. If you look at what the ONF has provided, there's this notion of TTPs, table type patterns, that are attempting to standardize these pipelines. But if you're still writing an application that's going to be generic, you've got to worry potentially about a dozen pipelines. And so flow objectives provide an abstraction so that your application doesn't need to be rewritten to each of those pipelines. And then finally, we have intents. These, rather than pipelines or anything, are just some example applications. You may have a Fabric application that needs to provide proactive connectivity, proactive connectivity mesh. You may want to do a converged packet optical LAN where you need to provision some piece of the network using Ethernet and some parts using optical connectivity. You may want to do L3, L2 combinations in an enterprise scenario. But if your application has a policy which is provide connectivity between 2 edge ports in my network, regardless of the underlying environment, the same application policy could be applied in multiple contexts. So on the programming front, we have multiple levels of abstraction. Depending upon the needs of your application, 1 or more of these may be appropriate. Finally, for the core abstractions, we have configuration. So there's network configuration. This is primarily a mechanism by which you can introduce new metadata, things like device names, location, properties of the devices that you wouldn't necessarily be able to discover. So any service application component can register to receive updates to configuration. They can inject new bits of configuration. This configuration can be made available through things like the UI and CLI. So for metadata, you can use the network configuration subsystem. On the device front, this is kind of where the boundary of southbound and northbound meets in the core. We have an abstraction that we call behaviors. Behaviors are a specific configuration task or set of tasks. For example, set up a queue or provision a port. And the idea with behaviors is that from a northbound, applications can interact with a generic model, and then the drivers would provide implementations that, given the device's capabilities and protocols, would result in configuration that gets pushed down to those devices. And then finally, we have dynamic configuration. This allows new Yang-based service models and device models to be injected at runtime. This is in progress. It's the work of the Dynamic Configuration Brigade. And it would enable applications to dynamically implement or translate these services. And so, as we mentioned in the TST panel, there's also some degrees of abstraction here. So dynamic configuration would be an example of enabling any model to be run anytime, sort of like a lower level flow rule type construct. You've got to be aware of the types of devices, potentially the protocols and firmware even of the devices, depending upon which models are supported across which devices. Behaviors are 1 level up. They provide sort of a generic abstraction for the types of behaviors that could be implemented by 1 or more models. And then network configuration is a little bit separate. So that's it from the core abstraction front. So in here, you can think topology and resources, network programming, and network configuration. We make these available through a number of external interfaces. So one would be the graphical user interface, enables you to get a view of a lot of this, and in some cases interact with devices. REST API provides the ability to do many of the same things. We've got some experimental gRPC APIs around topology. Those sit in the incubator now, but they're on the roadmap, as Thomas mentioned. Would provide similar functionality to REST. There's actually some cool things where if you talk to an endpoint, if you're HTTP 2 compliant, you can give them gRPC, and if they're HTTP 1 or 1.1, you give them REST. I think that would be cool for ONOS to do in the future, but roadmap item. And then finally, we have a CLI. This is primarily for administration or operators who need to gather some information and provide some configuration to ONOS at runtime. So these interfaces, primarily for the core abstractions, but as you'll find out too, they're also extensible by applications. So the final thing I wanted to talk about was extensions to the API. So you could call it ONOS applications or ONOS extensions. Extensions enable people to introduce new protocols, new drivers, new behaviors, and new integrations. And so any of these extensions, they can be loaded into ONOS, the same craft container. As far as they're concerned, they have direct access to the core APIs. They can expose APIs for other applications, and they can also augment the GUI, REST API, and CLI. Some examples of integrations would be for OpenStack, we've got ML2, we've got VTN, we've got integrations with XOS, which is part of the core project. So if there are orchestrators that have proprietary protocols, proprietary REST APIs, or what I mean by proprietary is they've got specific things defined by the orchestrator, you can certainly provide either a shim or fully fledged application for communicating with an external orchestrator or translating external requests into ONOS primitives. We've also got a number of new protocols that we've introduced. There's been contributions from the community for RabbitMQ as an alternate RPC mechanism. So gRPC would also fit in this bucket. For event streaming, there's a contribution of Kafka for receiving a stream of events. And then as far as metrics go, we've currently got applications for Ganglia, Graphite, and InfluxDB. So as there are new pieces outside of ONOS, its API is fairly extensible, either by directly opening ports, kind of like the protocols would, or by extending the REST API or future gRPC APIs. So that's kind of a whirlwind tour. I'm going to hand it off to Andrea, and then hopefully we'll have some time for questions at the end.
Okay. Thanks, Brian. I'm going to talk mostly about the southbound, so Brian covered the northbound. I'm going to cover from the network elements up. So right now, currently in ONOS, there are a bunch of southbound protocols. So these are the protocols that we can use to manage and talk and use devices, basically. So see, OpenFlow 1.3. 1.5 is in the works. We already have some optical extension in the code base. OVSDB, NatConf and Yang, as we discussed a lot this morning, Yang tools and Yang management system to deal with Yang models. We have SNMP, P4, that was something really cutting edge SDN technology with the Thrift API for the BMV2 soft switch. It was developed and demoed this year at SIGCOMM. There's BGP, ISIS, OSPF, interoperability with legacy networks. There's path computation element protocol that Huawei contributed, and the rest and the RESTCOM for devices, and the new Lisp that other people contributed to. So right now, what is a protocol? What is the definition of an ONOS protocol? Basically, an ONOS protocol is a set of features and modules that bring in what is needed to communicate to the device. They implement the standard set of operations that a protocol offer, for example, flow mods, group mods for OpenFlow, or the CRUD operation for REST, or the session configuration, copy config, set config, delete config for netconf. So this is the protocol. They're just dumb modules that provide you ways to communicate with the device, but they don't do anything without you asking for it. And they usually leverage third-party communication libraries like OpenFlowJ, or SNMP for J, Thrift for P4, something like that. And So they're loadable, as Brian said, and they're used by the providers. So here is where the real magic happens. A provider is there are southbound elements that are used to act or react on the network. So these are the classes that actually use the protocols that I told you about before, that are dumb, to actually do stuff. So for example, they react off up and down of devices with the device provider, and there is an open flow device provider, netconf device provider. So they're able to discover the device and tell the ONOS core, what is this device, what are his capabilities. Because you can see these providers, and I will tell you more about this later, as a level of abstraction between the core that has no knowledge of the protocol and the southbound that has the knowledge of the protocol, and how to deal with the abstraction that the core has on real devices. It alarm provider for notification and alarms, and they also provision the routes, the paths, the tunnels, all of the things that are needed to manage the network are done by the providers. So basically, we translate into device-specific commands for each protocol. Okay, so these are generals. Like in OpenFlow, everybody supports flow routes. So there's a flow route provider, a link provider, and like a lot of devices supports alarm providers. So that's general enough that we can create a provider. So what does a provider? How does a provider interact with the core? The core has a manager component that is replicated with a store, and with this manager component, the provider registers itself, obtaining a provider service. The provider uses the provider service to notify the manager of what happens on the network. For example, a device connected. The core uses the registered providers to do something on the network. And how we choose the right provider for the right set of devices? Basically through the device ID. The device ID in ONOS is actually a unique key per device that's comprised of a set of elements, but the first part is usually the protocol that you have to use to talk to the device. The manager uses that first part, that's OpenFlow colon, SNMP colon, netconf colon, to actually choose which provider to use for which device. And we provide also a set of fallback providers in the case where there's no way your device is going to go talk standard calls, or you have to do a very specific configuration for that device in order to obtain a general concept like a flow rule. Because as Brian said, the flow rule is just a match action, but netconf devices don't have match action idea of flow rule. They just maybe they can do enter that the traffic that enters port A outputs port B. So that you can do with maybe netconf specific calls. So we have those fallback providers to use drivers to enable this operations. So what is exactly a driver? A driver is a set of behaviors that can be activated on demand and is per device or per family of devices. It's identified by the driver name, the manufacturer, hardware version, software version. And it comprises a set of behaviors. So the behavior is an interface plus an implementation. The interface is general, just provision a port provisioning, okay? But the implementation is, let's say, Cisco port provisioning, Fujitsu port provisioning, netconf port provisioning with general devices, or Huawei port provisioning. And that depends on the device. And we can differentiate per device because we have the manufacturer, and that's going to be a company, and the hardware version and the software version. So if we have multiple devices, maybe same model of the device, but with a different software because they couldn't upgrade it, we can have different drivers for those devices. So what is a behavior? Brian stole my show a little bit before, but basically it defines the capability offered by that device. So it can configure ports, it can accept different pipelines, it can do different things. And it encapsulates that specific calls in there. So these device-specific calls are abstracted from the application's perspective, from the core perspective. And So basically, they just sit inside the ONOS core, and the application uses them to interact with the device for specific calls. So, as Brian said, both protocols, providers, and drivers are dynamically loaded through OSGI and our Apache Carafe structure that we have, and they're replicated across the cluster, and they basically are on demand, because let's say your network is completely comprised of OpenFlow devices. You don't care about any other protocol in the southbound of ONOS. You have OpenFlow and netconf, you use only those two. So you dynamically load and unload the providers, protocols, and drivers for the stuff you need. So you don't have to bring along a big bulk of code just because it's in ONOS, but you don't need it. You just activate it when it's needed. And so why did we do this modular structure? Because we want customization to happen here to be able to talk to different devices and manage the whole network equipment that's out there without having to change anything here. Because this is very important, that has the clean abstraction that Thomas and Brian talked to you about before. Because if we start customizing this to accept one or multiple of these devices, we're gonna basically leverage our network and our success on the success of one or two, three protocols. If this is general enough that you can just plug in multiple protocols, we can be successful independently of the success of devices, protocols, we don't care, okay? So it also enables us to be model independent always in the core and abstract this interaction with the devices to the apps. For example, in the intent subsystem, let's say you get a host-to-host intent. You just want connectivity from these two hosts. You don't care how that connectivity gets actually done in the network. And the path can be comprised of different devices between different protocols, but you get connectivity. So this is how we abstract to the application perspective all the dealing with the devices. Having this southbound core API where here a device is just a device. You don't have the notion of the netconf except for the device ID. But then the magic happens here, and then you talk to the device, but the application just see the result, okay? And this enables obviously testability, stability, and performance, because let's say you have a network and you want to test new devices with new protocol, you can still have your standard network, bring up the protocol in ONOS, bring up the device, and try that device. If that doesn't work, you cut it off, and your network is still up there. So that's it for me. And do you have any questions? I hope I didn't rush too much in my presentation.
I have a couple of questions.
We have like 5 minutes.
Okay, how different this is from MD-cell concept of
So it's the closest thing to MD-cell in this whole picture is the dynamic configuration subsystem. From the MD-cell perspective, everything's dynamic config. Models are introduced for the devices, device capabilities. Models are introduced for services, and MD-cell acts as a store and a brokerage, effectively, between various instances in the cluster and various applications that are interested. From ONOS's perspective, there are some what you could call more fixed function APIs for inspecting topology and doing programming that we've been able to optimize specifically for those use cases. So I guess what you could think is there's kind of this balance or flexibility where if you want to write a standard application, you can use the standard ONOS models and standard APIs. And if there's some random configuration or thing you need to touch, you can go down to that level. With the caveat that going to the device specifics could lead you to writing applications that are not necessarily portable across different hardware or different types of network.
And also,
sorry, what was?
Also, just to make sure, the MD-cell brings some dependencies across device models and protocols in the core of ODL. Here in ONOS, there's no knowledge of that. Here in ONOS is just pure Java objects, no notion of protocol, device-specific elements. It's just as general as possible in order for us to be independent of what you use here. Okay, so that's a little bit of the difference between the Yang model-driven core of ODL that brings elements in here that are auto-generated also and device-specific, and are completely protocol and device-independent distributed core. That's pure Java and Raft for the consensus.
Question.
Oh, I have just a small question. When you said that the Southbound interface going to open through 1.5 is going to be ready, my question is when?
That's a good question.
I don't have a date for you, unfortunately. but I will say that there are elements, there are pieces of 1.5 that people have built in on top of 1.3 as extensions. And so I know that there's been a couple of use cases on the optical side where they've taken some of the optical pieces out of 1.5, put it as vendor extensions in 1.3, and they've been able to build their use cases there. But I'm not.
Argela is working on moving forward.
Yes, I know that Argela company, for their use case, they need 1.3 and 1.5, so they're trying to implement the whole specific of 1.5 into ONOS, but we don't have a date yet. So that's why I said it's in the works.
But it's on the
Yeah. You had another question?
Who's going to assign the device ID?
What? Sorry?
Who's going to assign the device ID?
Oh, the device ID. So the device ID is managed by the provider. So basically, when a device comes up from the southbound, the provider reacts to this event and says, okay, you're a new device, you get this device ID. And since it's an open flow device provider, it knows that it has to assign the OF little piece. Plus, for OpenFlow, we use the MAC address. For netconf, it's IP and port. So that's a unique.
It's a URI, and the scheme of the URI is determined by the provider. In case of the OpenFlow, it's XTP to DPI, which does have a MAC address, but it varies. So it's of course possible if you discover device, same device through two different means. You will actually have two devices in the system with two different URIs.
So there's a question over here.
Yep.
You said that you need the providers and drivers to keep the core independent from the southbound.
Yes, absolutely.
What is the abstraction that you get from the southbound is richer or conflicting with the abstraction that you have? I'm thinking, for example, to stateful forwarding form. For example, in that case, of course, the model is slightly different, and this can have an impact on the form, right?
Yeah. So the idea is that we definitely give up some richness as we move up the abstraction hierarchy. That's why we have dynamic config that we're talking about, this notion of behaviors, and also extensions to flow rules. And so the idea is that when you have new rich functionality that's custom to your use case, you would treat it sort of as an extension that your application would need to be explicitly aware of. As those extensions become more popular, they're implemented in more devices and more standard, they can become part of the more standard ONOS APIs. So the idea is kind of exceptions are handled as exceptions, and then as they become more general use cases, they graduate. Yeah. Last question.
Yeah, last question.
Yeah, okay. You mentioned orchestration happens on top of the ONOS, correct?
Yeah.
Now, if you have like a Tosca-based application, that mapping is absorbed by the orchestration layer, not the ONOS layer.
Yes.
Yeah, Tosca.
Yes.
So ONOS doesn't see it at all.
No. So what's going to happen is the interface between your orchestrator and ONOS is going to be some either explicit rules or some explicit policy that is either in ONOS's terms or in the terms of an extension application that's going through the mapping to ONOS's terms. But in terms of orchestration, that policy would be handled by an orchestrator that's outside of ONOS, and its decision making is handed down to them.
Even the Northbound API doesn't have to worry about it.
Well, so maybe we should take the question offline so we can